Good afternoon, everyone. Are you ready? So now we're going to talk about reinventing federated learning operations on AWS. My name is Joe, and I'm a senior partner solution architect specializing on AI ML from AWS. And due to the settings in this room, I'm not able to turn on my camera, but the photo on the right side is pretty close how I look like. In many circumstances, you also might encounter that your customers, they are not able to move their data out their own premises, or they are not able to move the data out of their own region. And in that case, we are able to move the compute resources to the local data set. And then we are naturally going to think, hey, we are going to use distributed training. However, the distributed training strategies or the architecture we have seen today, just like a Lightning AI or like yesterday Anyscale or like a SageMaker distributed training, those distributed training architecture, they have those EC2 instances, or we also call the nodes. They're very, very closely coupled, which means that most possibly those cluster of instances, they are deployed in the same availability zone. And the reason is that they need to have high-speed training. They need to have a low latency for the training time. However, if we move those compute resources across different regions, and the training would be pretty slow. So basically, the current distributed training architecture, because they have those nodes or training nodes fully coupled, very, very closely coupled, they are not able to support the kind of distributed nodes across regions and to preserve the privacy. So that's why we have federated learning. So GDPR fines reached record high. European data regulators issued a record of 2.92 billion in fines, 2.92 billion euro in fines last year, up 168% on 2021. There are many privacy enhancement methods. There are a multi-party computation, federated learning, zero knowledge proof, differential privacy, etc. If we compare their transformer power, basically is machine learning relevance, versus the efficiency, we see that federated learning by far stands out among these options. So today we are going to talk about what is federated learning, why is federated learning growing in importance, and how to build a cloud-native federated learning operation framework on AWS. Federated learning is a distributed machine learning approach that trains machine learning models on distributed data sets. So it is able to leverage those distributed training, such as data parallelism and model parallelism we learned today for training across different distributed data sets. However, in terms of the architecture, it must be different. And it must allow the computer nodes to communicate across regions. Let's walk through an example. Imagine that there are 5 banks and each wants to fight crime. Each has their own data set, their own IT and machine learning systems, and their own fraud patterns. However, many banks discovered that some banks might uncover fraud patterns that others have not. So if all these banks put their knowledge together to train one global fraud detection model, they would fight financial crime much better than any of individual banks. But the problem is that none of these banks like to share their data because their data contains sensitive customer information. And the banks might be competitors in the meantime. So federated learning provides a mechanism for them to collaborate. to train a global model without sharing data. So here we have a few terminologies. On the left side, we can see we have a few federated learning clients. And they have their own local data set, their own local training facilities, and generate their own local models. And those clients can be on premises, can be edge devices, and can be on cloud. And on the right side, you will see we have a federated learning server. The server is to aggregate the local models collected from the clients and then aggregate them to our new global model. So in the beginning, the federated learning server sends out an initial global model to the clients. And individual clients will train the model based on their own local data set and generate their own local models, and then send the local models back to the server. And then the server aggregates them into a global model, which is then sent back to clients. So this is a single federated learning training round. And there can be hundreds of training rounds in order to reach certain accuracy, or maybe you define that you need how many federated learning training rounds. So as a result, the global model, the final global model, typically or usually will perform better than individually trained models. There can be different flavors of federated learning based on what the features are in those distributed local data sets. There are horizontal and federated learning and the vertical federated learning. In horizontal federated learning, each distributed data set has the same set of features. And in this example, the example on the left side, you will see that we have bank 1 and bank 2, and both banks have the same features that are custom ID, age, and zip code. While in the vertical federated learning, each distributed data set has different set of features, but with overlaps and the ability to map to the same record. So for the example on the right side, you will see the vertical federated learning example. We have bank 1 and bank 3. And both banks, actually, they only have a single common feature, which is custom ID. And they have different other features, such as age and zip code for bank 1, and then age range for income for bank 3. And based on how federated learning clients are interacted between each other, we have hub and spoke and peer-to-peer. For the hub and spoke architecture, there is a central federated learning server talking to a group of federated learning clients. And for the peer-to-peer architecture, there are only clients. They are mesh connected, and they are peers. And based on when to aggregate at the federated learning server, we can have a synchronous and asynchronous federated learning. So in synchronous federated learning, the server waits for a set of local models to be ready, and then aggregate them into a global model. For the asynchronous federated learning, the server immediately updates the global model whenever a local model is received. So why is federated learning important? We have observed 4 benefit patterns of federated learning. The first pattern is cross-device, where thousands or even millions of devices, such as mobile devices, collaborate together to train a global model. The benefit is for privacy preservation. The use case areas for cross-device include edge ML, retail, and automotive use cases. And the second pattern is cross-silo, where tens or hundreds of organizations and companies, they work together to train a better model. These organizations or companies, they might already have their own data set and their own individually trained models. But they can use federated learning to train a global model that is more accurate. So the benefit is for performance. And the use case areas include inter-institutional collaborations, especially in the healthcare industry, and also financial service industry and the government projects. And the third pattern is intra-region training. Due to data localization regulations that we cannot move the data out of the region, and also due to operational challenges or high cost of transferring a large amount of data to a central location for training. And federated learning can be used to train models across distributed datasets from different regions and even within the same organization. So the benefit here is for cost saving. Its use case areas include applications requiring global reach. And in this case, machine learning with a larger data size and relatively smaller machine learning models benefits more, since exchange smaller machine learning models save more data transferring cost. And the fourth pattern we have observed is hybrid cloud that provides operational flexibility for data, because data can be on premises or can be on the cloud. So in this scenario, we can keep data with high sensitivity locally, and we may have augmented data in the cloud, and then we can provide some efficient bursting. We have seen federated learning applied to different vertical industries, such as financial services, life sciences, industrial AI, public sector, telecommunications, and transportations. There's still many challenges in federated learning. One key challenge is data heterogeneity. For example, one dataset has only all the cat images, and another dataset has all the dog images. Data heterogeneity impacts the accuracy of the global model, leading to more training iterations and longer training time. Many solutions in the literature have been proposed to mitigate the impact of data heterogeneity. Then the second key challenge is privacy preservation. The local models and the global models exchanged between the server and clients may leak private information via reverse engineering. And many privacy preservation approaches also have been proposed for federated learning, such as secure aggregation, differential privacy, and homomorphic encryption. And the third key challenge is federated analytics. Federated analytics provides statistical measurements of distributed datasets without violating privacy requirements. It is very important not only for data analytics across distributed datasets before the training, but also for model monitoring at the inference. And despite the key challenges of this federated learning algorithms,
Joe, sorry for interrupting. Can you get closer to the mic or something? Because some people here say the voice is not very clear.
Okay, apologize for that. Yeah. Can you hear me better?
Yes, it's better. Yes, thank you.
Okay, apologize for that. Okay. Despite the key challenges of those federated learning algorithms, it's also critical to build a secure architecture that provides end-to-end federated learning operations. And this architecture must coordinate federated learning server and the clients for model building, training, and deployment, and must support CI/CD, continuous integration and continuous delivery. And the challenges for building such architecture may include memory and computational constraints, cost optimization, and the billing allocation among the server and clients. So let's talk about how to build federated learning operations. Here we show the steps for federated learning operations. On the right side, we have the federated learning server, which includes the aggregation server and also a model registry. And on the left side, we have a single federated learning client, but actually we can have hundreds of federated learning clients. And Federated Learning operations need to provide continuous integration and continuous delivery. Therefore, we need a code repository, which is on the bottom, and for the server and the clients to agree on certain things. They include customized algorithms for Federated Learning, such as here, the aggregation, the server aggregation.py, which is the aggregation algorithm implemented at the server. And we also need to have them agree on a global model for training, and also agree on certain configuration information for the server and the clients to interact with each other. Now, let's start. So step 0 is to set up the Federated Learning server and clients. After them downloading the Federated Learning package from the code repository and trigger a Federated Learning training task. And any change in the code repository, once agreed upon clients, may trigger a new Federated Learning task. And step 1, after Federated Learning task is triggered, the server notifies the clients that, hey, the global model is ready. And then step 2, Federated Learning clients download the global model from the Federated Learning model registry. And then step 3, clients start local training, and the local training generates local models. And step 4, Federated Learning clients upload their local models and the local model information to the Federated Learning model registry. And the local model information may include the number of samples in the local dataset, client ID, and the local training and the testing accuracy, etc. And step 5, once there are enough local models collected at the Federated Learning model registry, the server aggregates the local models into a new global model and writes it back to the model registry. And step 1 to 5 is a single Federated Learning training round. And there can be hundreds of Federated Learning training rounds until the number of Federated Learning rounds reaches a threshold, or until the global model reaches certain accuracy threshold. So once the global model is finalized, step 6 is to deploy and monitor the final global model at inference sites. So we can see that the server actually behaves like an orchestrator. It performs a very important role. So who can or should be the Federated Learning server host? Or who can be trustable to be? It can be one of the clients, can be all of the clients, or can be none of the clients. For the case where none of the clients to be a server, then it can be the private third party, can be the government, can be the clearing house and the credit bureau. However, billing, trust, and access control of those services and among the server and the clients needs to be carefully considered, and the contractual agreements may be needed. Yesterday, we have also discussed about ML ops. So what are the differences between FL ops and ML ops? In ML ops, we know there are 3 basic steps: centralize the data preparation, centralize the training and tuning, and then model deployment and monitoring. In Federated Learning operations, actually we have parallel data preparation at different clients. So it's distributed way. And then we have Federated Learning, which is a distributed training. And then we have model deployment and monitoring. So actually the last step, the model deployment and the monitoring for the global model, can reuse the step from the machine learning operations. Now let's see a demo. So in this demo, you see we have 3 windows. The one on the left is the server. And the one is actually a step functions. And the one on the right side are two clients. Client 1 is under the same account as the Federated Learning server, and client 2 is at a different account from the Federated Learning server. This simulates a typical scenario where we can have a Federated Learning clients from different organizations or different regions, and the different AWS accounts. So in the beginning, we can see the step functions. There are multiple steps which are running at Lambda functions. And we can see the clients, both clients have the same directory architecture. There are code repo, which contains the code downloaded from the code repository. And we have local data sets, and we have local models. And we also have some Python script for running the Federated Learning clients. And we also have the local data processing Python scripts for having their own local data processing. Let's see what's under the code repo. Basically, it is the global model that agreed among the clients and the server. And also we have the configuration file, which to help the client and server to interact. We can see here the client 2 has a cross-account roles to assume in order to access the service at the server. Well, client 1 does not have because it's under the same account of the server. Now let's start the training. So we start the client 1. It's under local data processing, and we start client 2. So both are processing their local data sets. Now at the server side, we're going to execute the step functions. So the first step is to initialize, basically is to initialize the services at the server side. And after that, the server going to send out the notifications to the clients that, hey, the global model is ready, let's start training. And then on the right side, we can see at each client, they started the Federated Learning training round from 0. And you may also see there's a task token. The task token is corresponding to a specific SNS notification sent out from the step function. And we call it a callback task token. By doing that, the step function is basically going to pause and wait for this token to come back. Okay, now step 1 is to receive notifications at the client. Step 2 is to download the global model. Step 3 is local training at the clients. And we can see the accuracy of testing and the training are printed out. And now we are at Federated Learning training round 2 and 3. Okay, local training. And step 4 basically is to upload the local models to the server. So you might also notice that after each Federated Learning training round, the accuracy improves gradually. At the server side, we can see that we have got some green steps, and there is a step which check the constraint if it's satisfied. So the constraint we set here is the number of training rounds is equal to 8. So we start from Federated Learning training round 0, and then it will stop at the Federated Learning training round 7. So once this condition is satisfied, it will go to the step of yes, end training. If it's not satisfied, it will continue the next Federated Learning training round. Now we are at training round 5. Okay, we are at the training round 7. That's the last training round. Now, the Federated Learning training is finished, and the final model is ready. And we are at the step 6, which is to download the Federated Learning trained global model, and then we can deploy it by MLOps. So how to build this demo? So here we show you AWS reference architecture, which shows the AWS services that we used to build such Federated Learning training architecture. And it is a cloud-native Federated Learning architecture. And we have a Federated Learning server on the AWS, which is on the right side. And we also have a client on the left side. And we have one client, which is on premises. And we have one client on AWS cloud. On the server side, we have AWS step functions to iterate each Federated Learning training runs. And for each training round, the step functions sends out SNS notifications along with a callback task token, which I have shown you in the previous demo. And then the step functions pause and wait for the task token sent back. And the notifications is then queued at a few Amazon SQS queues. Actually, each Federated Learning client has a corresponding SQS queue. And then here we also have a Federated Learning model registry, which is on the top. It consists of Amazon DynamoDB and Amazon S3. Amazon S3 is for storing the global model and the local models, because model can be very large. So we use S3 to store them. And we also have DynamoDB is for storing the local model information. Like we have mentioned before, it can be the training round ID and the client ID and the number of samples at each client and the testing and the training and testing accuracy of the local models. And the DynamoDB actually storing those information and also can provide the traceability for Federated Learning. And in the meantime, we also enable DynamoDB stream associated with this DynamoDB to trigger AWS Lambda. This Lambda is for model aggregation. So whenever there is a new local model written to the S3 and the new record is written to the Amazon DynamoDB, and then this Lambda will be triggered. It will check if there are enough local models collected. If there are, it will start to download those local models from the S3 and aggregate them and send back to this S3. So if not, then the Lambda function does nothing. So once the Lambda function computes or aggregates the local models into a new global model, the model is written back to the S3, and in the meantime, the Lambda function sends back the task token so that the step functions continues to run. And then the step functions will determine if the Federated Learning should be terminated based on the constraints specified. And for example, if the number of training rounds reaches threshold, and then the step functions will terminate. And on the client side, we can see we have our on-prem Federated Learning client. It uses AWS SDK and CLI to securely access the services at the server because it automatically provides data protection in transit. And for the client's own AWS cloud, we can use a private link for data protection. This is this architecture has a few advantages. So first, it is a cloud-native architecture, which means that it can be deployed with infrastructure as code tools, such as CDK. And actually here we deploy it by CDK. And it is built from ground up for Federated Learning so that you are able to run customized Federated Learning algorithms in these cloud services. For example, if you have new models or you have new aggregation algorithms, you can actually create a new Lambda function for your new aggregation algorithms. And it is a cloud native, which means that it's also very easy to integrate with other cloud native services. For example, if your customer would like to have authentication for the Federated Learning clients who are going to join the training, you can leverage AWS Cognito for authentication for those clients. And if your customers want to trace the Federated Learning and trace those services, you can leverage CloudWatch and CloudTrail to see the utilization and tracking the services and to track those transactions. Second advantage is that there is no direct write from the server to the clients. Instead, you may notice that the clients are able to pull and push information from and to the server services based on their own willingness. The reason we design this way is that first, it gives the client flexibility of join or not join certain training rounds because clients might be busy. You don't want to join for certain training rounds. Another one is that it provides the privacy of the client's IT and the machine learning systems. They don't need to expose their IP addresses. They don't need to expose their services to the server. Instead, they just access the services. And then the third advantage is that the Federated Learning server uses serverless services instead of using a persistently running Federated Learning server, which reduces the computation cost at the server side. So far, do you have any questions? Okay.
Any questions?
Okay. Despite the challenges in Federated Learning, we see tremendous potential. Increasing regulatory pressure on machine learning will also broaden the applications of Federated Learning. And even in large language models, which is a fast evolving space, Federated Learning experiments are showing promising signals. And we would like to invite you to run solutions on this architecture. And we would love to co-build with you for the challenges and different architectures. And actually, you might notice today the demo we have used data parallelism, which is a distributed training strategy we learned today. It actually implements data parallelism. However, where's the model parallelism? Actually, we worked with a partner, which is one of which is a telecommunication partner on the model parallelism. Basically, we call it a vertical Federated Learning. We built that vertical Federated Learning architecture with that partner, and soon we are going to have a machine learning blog published about it. And we would love to work jointly with you on your use cases. And email us if you would like to, work with us on your customer's use case. And here's my email. And again, I will be happy to discuss with you further and discuss with you those use cases or solutions you would like to run. Thank you.